In this lesson, we're going to focus on steps 3 and 4 of our hypothesis testing. And then in the next section, we're going to pull it all together and do some examples of hypothesis testing with all 5 steps. But right now, we're going to really focus on steps 3 and 4. And steps 3 and 4 is where we're going to actually use the tools that we need in order to decide whether we're going to reject or not reject the null hypothesis. So step 3, we're going to use a method called rejection region. And then in step 4, we're going to use a p-value method. And they should both give us the same results, but think of it as a way to double check ourselves. We're doing it 2 different ways to double check that what we're doing is okay. So when we use the rejection region, there's 3 possible situations we could run into. Now, the first thing that we need in order to figure this out is we need to look at what's called our level of significance. And it's usually noted with the Greek lowercase a, which is this alpha here. And that's called our level of significance. This is going to be a preset percentage that will help us give us like a cutoff point. So in this example, I'm going to use a level of significance as 5%, which it can also be written as 0.05. This is a pretty common one. The other common level of significance that is used pretty often is 1%, which would be written as 0.01 as a decimal. Now, the first case, when we're doing the rejection region, you could have what's called the left-tailed test. And when we do a left-tailed test, that means the focus is going to be on our left tail. Now we're going to use our level of significance to determine the cutoff point. So since our level of significance is 5%, that means I want to find this critical value here. I'll just label it generically as C for critical value for right now, so that the area under the graph here to the left, because we're doing a left tail test, is 5%. So the rest of this is going to be 95%. Okay, now, if the test statistic falls within the rejection region, that's the red. So let me label that. So red is the rejection region. When we calculate our test statistic, we are going to look to see if it falls within our rejection region. If it does, I'll color code this. If it falls in the red, then we're going to reject the null hypothesis. If it falls outside the rejection region, then we're going to say do not reject the null hypothesis. So that's the left-tailed test. Now it's pretty much the same idea for right-tailed. It's just we're looking at it on the right side of the graph now. So we're going to look for our critical value. And because our level of significance is 5%, we're looking for a critical value that gives us 5% to the right. And so that shaded red area is going to be our rejection region. So if it falls in the red area, we're going to say reject the null hypothesis. If it falls anywhere else, we're going to say do not reject the null hypothesis. Okay, the last situation you could run into would be two-tailed. It's very, very similar. If we have a level of significance of 5%, that means if we're doing two-tailed, we want that to be split up between 2 tails. So that means I'm looking for where this is 2.5% and this is 2.5%. And these are going to be our rejection regions. In this case, since we're looking at both tails, it could fall in either tail, and we split that percentage up between the 2. And then the leftover, where we don't care if it falls, That's our 95%. So again, if it falls in the red area, in our rejection area, we would say reject the null hypothesis. And if it doesn't fall in the red area, then we would say do not reject the null hypothesis. So this is the rejection region method, and we need to know what our test statistics are for this. And so when we go into examples, I'll go into it more detailed. I just want you to understand the concept of this for right now. Now let's look at step 4, which would be using a different method to double check our answer and to double check our decision from step 3. So I haven't mentioned this yet, but when we look at the level of significance, that's our alpha, that's the probability that we reject the null hypothesis when in fact it's actually true. And we're going to use that alpha again in the p-value method. So when we use the p-value method, that is when we take the sample statistic and we compute the probability that we're going to get another sample statistic that's as extreme or more extreme than the test statistic computed from the random sample we already have. So if the p-value is less than or equal to the level of significance, we are going to reject the null hypothesis. And we're going to say that the results were significant. Otherwise, we're going to say that there is not enough evidence to reject the null hypothesis. So let's go through and look at the 3 situations with each of the kinds of tests and how we're going to handle it with left, right, and two-tailed. So when we calculate the p-value, what we're doing is we're finding our test statistic, which will give us a cutoff point. Then what we're going to do is we're going to use our knowledge of probability, and we're going to find the probability that we get another test statistic that lies in that red area. That's the probability that we get another test statistic, I'll just call it X, that's less than or equal to the test statistic that we already have. This is our p-value. So if we get a p-value that's less than or equal to our alpha value, our level of significance, we are going to reject the null hypothesis. If the p-value is greater than alpha, then we're going to say we do not reject the null hypothesis. Now the same idea is true for the right tail test. It's just going to be on the right-hand side. We're going to use our test statistic to find this probability here in red, that the probability of getting another test statistic that falls in that red area, that's our p-value, that's our probability. And again, if that p-value is less than or equal to alpha, then we're going to reject our null hypothesis. And if the p-value is greater than alpha, we're going to say do not reject the null hypothesis. Now for a two-tailed test, again, it's the same idea, but it's going to be split between the two tails. So we're going to get a test statistic, and then we're going to use symmetry to find that spot on the other side of the graph. And then these two areas here are going to add up to be my value of p. This is going to be my p-value divided by 2. This is going to be my p-value divided by 2 because it's got to be split between the two tails. And then again, when we look for that p-value, we're looking to see if that p-value is less than or equal to alpha, we're going to reject our null hypothesis. And if my p-value is greater than alpha, we're going to say do not reject the null hypothesis. All right, in this first example, it talks about Rosie, who's a sheepdog. She gets regular checkups from her owner in the vet, and the vet is concerned that her heart rate is slowing down. Based on the vet manual, dogs of this breed should have a mean of 115. And then she also knows from past experience that the population standard deviation is 12. And so the vet is concerned her heart rate is slowing down. So over the past 6 weeks, the vet took some data, found her heart rate in beats per minute, and now when she found the mean of that sample, she got 105, and she wants to use a level of significance of 1% to determine whether or not the dog's heart rate is actually slowing down. So the first thing that we're going to do is we're going to establish our null and our alternative hypothesis. So our null hypothesis is if nothing has changed, if her mean heart rate is 115 beats per minute. Now, what the vet is concerned about is that her heart rate is slowing down, so she wants to check to see if her mean is less than 115, which tells me I'm looking at a left-tailed test. All right, now, when we're doing this, because we were given the population standard deviation of 12, we know that we're going to use a normal distribution. So, and we're doing this for a sampling distribution because it's talking about taking samples and the mean of that sample. So we're talking about X bars, which means my standard deviation for X bar is going to be 12 divided by the square root of the sample size. Our mean is 115 in the center. And because we're doing the normal distribution, our test statistic, and I'm going to label it with a T down here to remind us that this is our test statistic so we don't get it confused with our Z critical. It's going to be your X bar minus the mu divided by our standard deviation. So when we put this in terms of a standard normal curve, we know that the center is 0, and I'm going to use, the first thing we're going to check, we're going to use the rejection region. So to find the rejection region, because we're doing a 1% level of significance, I want to find this cutoff value here so that my rejection region contains 1% of the area under the curve. So I need to find my Z critical for that cutoff point. And to do that, I'm going to use inverse norm. I'm going to put in my percentile to the left, which is 0.01. Since we're doing this standardized, I'm going to put in 0 and 1 for my mean and standard deviation, and I'm going to get negative 2.33 if I round to 2 places. So this Z critical here, my cutoff point, is going to be negative 2.33. So the non-rejection area would be this blue. So the question is, I got to find my test statistic and find out which side it lies on. Is it in the blue or in the red? Is it in my rejection region or not? So I'm going to find my test statistic. I'm going to put in my sample mean, which is 105, minus my mu, which is 115. And I'm going to divide by my standard deviation over the sample size. So that's going to be 12 over the square root of 6. All right, when I find my test statistic, I'm going to find that it's negative 2.04. So when I look at my graph, here's Z is equal to negative 2.33. Here z is 0. So if I look at this in terms of a number line, negative 2.04 is going to fall in between. This is my test statistic, my negative 2.04. That doesn't fall in the rejection region. It's falling in the blue area. So we're going to say do not reject the null hypothesis. So this is using the rejection region method. Now let's practice using the p-value method. Okay, for the p-value method, here's our center, which if we're looking at it in terms of raw data would be 115. For the p-value, I'm going to put my test statistic here, and we found that to be negative 2.04. So what I want to do is I want to find this probability. What's that probability? And then I want to check it against my alpha, my level of significance. So I want to find the probability that any other value of z that I find is going to be less than negative 2.04. This is what I'm looking for. I'm looking for that value, that probability. So I'm going to do normal CDF. This is all standardized, so you can just put in the standard deviation is 1 and the mean is 0. I'm going to put in that my lower bound is negative 1E99 and my upper bound is negative 2.04. And my mean and standard deviation is 0 and 1. Okay, when we put that in on the calculator, we're going to find that that probability is 0.0207. So this is our p-value. And that represents this shaded area over here, the probability of getting less than negative 2.04. Okay, so now we got to compare our p-value to our alpha. My p-value, we said, was 0.0207. My alpha level was 0.01. Since 0.0207 is greater than 0.01, we're going to again say, do not reject the null hypothesis. We only reject the null hypothesis when the p-value is less than or equal to my alpha, which in this case is 0.01. So overall, when we check both methods, both of these decisions that we came to was do not reject the null hypothesis. In the second example, it says there's a drug, 6MP, that's used to treat leukemia. And the following data represents the emission times in weeks for a random sample of 21 patients using the drug 6MP. So all this data was collected, and then it says let X be a random variable representing the remission time in weeks for all patients using this drug 6MP. We're going to assume that the distribution is mound-shaped and symmetric. A previously drugged treatment had a mean remission time of 12.5 weeks. Does the data indicate that the mean remission time using this drug in either direction, it's just got to be different, is it different than 12.5 weeks? And we're going to use a level of significance of 0.01. So the first thing we're going to do is we're going to set up our hypotheses. Our null hypothesis is going to be that the mean is 12.5 weeks. That's this information here. Now, because it says we just want to see if it's different than 12 weeks or 12.5 weeks, the alternative hypothesis is going to be that the mean is not 12.5 weeks, which tells me this is going to be two-tailed. Now, nowhere in the information that's given to us are we told what the population standard deviation is. We just have the information from the sample, which tells me that we're going to use the student t-distribution and our test statistic. And our test statistic is going to be t, and we take the mean minus the mu, divided by the sample standard deviation over the square root of n. This is going to give us our test statistic. Now, I did this ahead of time, and I know that the x bar is 17.1. If I don't give that to you, though, you're going to have to put that data in on your calculator and find that using your one variable stats. All right, so we have that the mean for the sample is 17.1. We're going to subtract the mean, which is 12.5. We're going to divide by the sample standard deviation, which you would also get from your one variable stats, which is, I got that to be 10. So I'm going to take 10 over the square root of 21, which is our sample size. Now, when you put that all in on the calculator, you're going to get approximately 2.108. All right, now, the student t-distribution, we know that's similar to the normal curve. It just has wider wings. So here's our curve. My test statistic is 2.108. Now I have to find my rejection region. So I need to find my cutoff points here and here for my critical values. And I want this to be split up between two wings. Now I want there to be a 1% level of significance. So when I split that 1% into two halves, that's going to give me 0.005 on either side. So I'm going to have to use inverse t now to find those critical values. For my t critical, I'm going to use inverse t. I'm going to put in my area, which is 0.005. That's my area to the left. And then I put in my degrees of freedom. Remember, your degrees of freedom is the sample size minus 1. Since my sample size here is 21, I'm going to put in that my degrees of freedom is 20. Okay, when I hit enter on my calculator, I'm going to get that this is negative 2.845. So I'm going to get for this side over here, this t critical, I'm going to get negative 2.845. And then because it's symmetric, this is going to be the same thing on the other side, just positive. So 2.845. So there's my rejection region set up. All right, now if I take my test statistic, which we found was 2.108, that's going to fall, here's 0 in the center, that's going to fall somewhere in here. That's my test statistic. So that's 2.108. Because that doesn't fall in the red rejection area, we're going to say do not reject the null hypothesis. Now to find the p-value, I'm going to find the area of one of these shaded red areas and then multiply it by 2 because there's 2 of them. Because I want to find the probability that it will land in either one of these wings. So I'm going to take 2 times the probability that you get a value of t that's greater than 2.108. Now, on the calculator, I'm not sure, I don't remember showing you this before, but there's a t-CDF function, just like a normal CDF, where you can calculate areas under the curve on a student t-distribution, and it works the same way as the normal distribution. You put in your lower and your upper bound, okay, and your degrees of freedom. So you would use, let me write this down. So you would use T CDF, and you would put in all the information. And then your first piece of information would be your lower bound, then your upper bound, and then your degrees of freedom. When you find your value for your TCDF, that's going to give you the probability of just one wing. And what you get is 0.0239. And when I multiply that by 2, you're going to get a p-value that is 0.0478. This is your p-value. And don't forget, we multiplied it by 2 because we found the probability of just one wing, but because we have 2 wings, we had to double it. So here's our p-value. Now the question is our p-value less than or greater than the alpha? Remember, our alpha is 0.01. That's our level of significance. Our p-value we just found here is 0.0478. So our p-value is greater than my alpha, which tells me do not. In this example, it says a team of eye surgeons has developed a new technique for a risky eye operation to restore the sight of people blinded from a certain disease. Under the old method, it is known that only 30% of the patients who undergo this operation recover their eyesight. Suppose that surgeons in various hospitals have performed a total of 225 operations using this new method, and out of that 225, 88 have been successful, meaning they fully recovered their eyesight. Can we justify the claim that the new method is better than the old one, and we're going to use a 1% level of significance again? So in this example, we're talking about proportions. We're looking at a success rate. So when we set up our null and alternative hypothesis, we want to look to see if nothing has changed, what's our proportion? Previously, we have that our proportion is 30% or 0.30. Now, if this new operation is improving the success rate, then our alternative hypothesis is going to be that our success rate is greater than 30. So this is going to give us a right-tailed test. And we're dealing with proportions here, so we want to check to see if our sample size is sufficiently large enough to be able to use the normal distribution here. So remember, we have to check n times p if that's greater than 5, and if n times q is greater than 5. So our sample size is 225. When we multiply it by our success rate, that's 0.3, we want to check to see if that's greater than 5. When we take that and multiply it, we get 67.5. So that works. Now let's check our Q. So we have 225. So we have 225 times the complement of P, which is 0.7, and we want to see if that's greater than 5. When we take 225 times 0.7, that's going to give us 157.5, which is also greater than 5. So this works, which tells me I can use the normal distribution here. In my test statistic, when we're dealing with proportions and I'm using the normal distribution to approximate, our test statistic is going to look like this. We're going to take our P prime from the sample, subtract it from our proportion, and then divide by the standard deviation, which is PQ over N, and then square root it. So let's find our test statistic. If we take 88 out of 225, that's our P prime. That comes from the sample. That's going to give me a proportion of 0.39. So I'm going to take 0.39 minus my 0.3, divide it by the square root of 0.3 times 0.7 all over 225, and I square root that whole thing. That's a big mess, so be careful when you put that in on your calculator. Put parentheses in the appropriate places to make sure that you get everything right. Now, when you put that in on your calculator, you should get 2.95, and that's an approximation. So that's our test statistic. Now, let's look at our rejection region. Since we're doing a 1% level of significance, I want to look for a rejection region that has an area of 1%. So I'm going to find Z critical based on that. Now, when I put that in the calculator and do my inverse norm, I'm going to get 2.33. Now, looking at our test statistic, we got 2.95. So that is going to be in the shaded area because it's greater than the 2.33. When I draw my test statistic on here, my test statistic is going to be over 2.33 because we got 2.95. So that's going to be in the rejection region, which means we are going to say we're going to reject the null hypothesis. Now let's look at our p-value method, and we want to make sure that our decision for the p-value method syncs up with what we did for the rejection region. So for the p-value method, we're going to graph our test statistic, which we said was 2.95. And then we want to find the probability that if we pick another sample, that proportion is going to fall in that red area. So we want to find the probability that Z is greater than 2.95. I'm going to put that into my calculator, and I'm going to find that the p-value is 0.0016. Now, our level of significance, our alpha, is 0.01. So our p-value is less than my alpha because 0.0016 is less than 0.01, which tells me I'm going to reject the null hypothesis. And that matches up with what we got when we did it using the rejection region method. So we know we're on the right track. So we covered how to work through the rejection region method and the p-value method. That's step 3 and 4 of our hypothesis testing. The last step then is to write a complete sentence and interpret our results. So that's what we're going to do in the next section. We're going to pull all of this together and we're going to work through some hypothesis testing, all